Hey, it's Steve. Welcome back. Now, I spend a lot of time on YouTube, obviously, and a lot of it is to read comments from my viewers, but I also spend quite a bit of time reading comments on other YouTubers' channels, as well as other YouTubers' comments, and frankly, I'm getting a little annoyed by some of the misinformation that I've seen happening. So in this video, what I want to do is look at 5 of the most common myths related to these diode lasers, and dispel some of those rumors and hopefully give you a little better understanding of both how the laser works and whether all these comments you're hearing are true or not. So let's get started. Now, most of the myths I want to dispel in this video relate to laser power and how the laser reacts to that power. So what I did was I went to my storage bin and I dusted off a few lasers, because what I want to do is cover the range from 5 watts to in this case 33 watts. You could certainly go higher, but you'll see that things are pretty much the same. And I lined up 4 lasers that I really span this range. So first on the list is the SculptFun S30 5 watt laser, and it'll be our test case. Next I have the Creality Falcon 10 watt laser, and third on the list is the Longer Array 520 watt laser. And finally, I have, since I had it in the shop, the ACMER P2 33 watt laser. All right, so most of the tests I'm going to do relate to cutting, and that's because that's where most of these myths start. And I popped up a list of measurements I'm going to take here. So the first one is a simple calculation based on the beam power and the beam size. What is the energy density of that particular beam? Then I'm going to do a standard material cut test, and I'm going to run that exact same test with the exact same settings on every laser. Then I'm going to do a fastest cut test, and to stack things up to make it simple, the thing I'm going to cut is a kerf test, and then I can measure the kerf as well. So those are the tests, and it will be really simple, and you can reproduce this on your own laser if you want. Now, along with the tests, I wanted to lay down a couple of guidelines here so you know that I'm on the up and up here. First, I have no vested interest in which laser wins. This really isn't about winning and losing. It's about understanding the characteristics of each of these lasers at these given powers. Next, the focus here is on the actual laser, not the performance of the overall product. So in cases where the laser supports air assist, I won't be using it. It will just be the laser working on its own. And finally, each test that's performed here, and I'll show you some of the results, each test that's performed here will be run on exactly the same piece of material. I bought a big slab of 1/8" plywood from a local hardware store and cut it up into squares, and those are the things I use, so that all of these things come from the same exact piece of material. With the test criteria out of the way, the very first thing I did was run a material test on each of these lasers. Now, it wasn't just any test. I ran the exact same test on each of these lasers, and I'm showing it to you on screen here because I want to be able to have you test this on your own laser. And I went from 70 millimeters per minute up to 700 millimeters per minute, and power on the horizontal from 10 to 100%. And that gives us 100 squares to look at, and some of them on each of these lasers will be cut out and some certainly won't. Now, keep in mind that this is material sensitive, so I'm using, again, typical 1/8" hardware store plywood. If you're using a different material, you may have to adjust these ranges a bit, but hopefully you can find something similar. So I ran the material test on each of the 4 lasers in the test group, and the first one is the 5 watt, and you can see it did cut some out there. Now the scale is wrong there, it's millimeters per second, but it's the same speed. The 10 watt cuts quite a bit more than the 5, the 20 watt certainly cuts more than the 10, and the 30 watt cuts the most. And this isn't surprising, but it's something we'll roll into the results and we'll talk about as we're talking about some of these myths. The last piece of information we need to dispel some of these myths is a kerf test. And I killed 2 birds with 1 stone here, so I determined the fastest speed that I could run the test and cleanly cut through the material so that I could then measure the kerf. And while I was doing that, I actually timed the test, so we get a good choice of both the kerf and the time it took to run it, so we can determine how much faster or slower a given laser of a certain power is. There wasn't a whole lot of testing and data collection I needed to do to help dispel some of these myths I'm going to talk about, But I rolled it all into this table, and you can see the first two rows here come from the manufacturer's spec sheet. The power can be a bit dubious because manufacturers like to mislead us a bit, but I did my best to determine what the actual power at the output of the tube is, as opposed to what the manufacturers sometimes do, which is add up the number of diodes in the box. There will be some loss, and I'll talk about that later, but it's generally pretty close to what the manufacturer is telling you here. The spot size, you can see there's two camps here. There's the 0.06 millimeter square beam size, and then the quote-unquote giant, by some people's measure, 0.08 by 0.1 millimeter beam. And I use those two numbers to calculate the energy density. Now, what this number actually is to say if the beam was 1 millimeter square, how much energy would be in that beam when hits the material. And you can see from the left end, where we have a low power laser, to the top end, the 33 watt is roughly 4 times the power energy density as the 5 watt laser. The cut tests were all run at 100% power, and I determined through some experimentation the absolute fastest I could run on this material and get a clean cut through. And the thing I was running, of course, was the kerf test, so I got the kerf measurement out of it as well. And you can see the speeds there for each of these lasers, and again, from the lowest end to the highest end, we're almost an order of magnitude faster. The kerf test, there is this perception that small beams create little kerf, and it's easy to argue that, except that when you look at the results of, say, the Sculpfun S30, the kerf is relatively huge compared to all the rest. And at the far end, the ACMER P2, the beam kerf was really 0.162 millimeters. So it wasn't as terrible as people would like to believe. And some of this you can tweak with focus. Potentially, sometimes the automatic focus measurement that manufacturers use isn't exactly accurate, but I used what they gave me, and I came up with these numbers. All right, all the data has been compiled, and it's in that table down below, and I'll leave that table up while we're talking about the myths as I'm trying to knock these down. I'll start with this first one, and it's this. The real laser power that's reaching the material doesn't change a whole lot based on the size of the laser module. Now, this one is bogus. I don't know where this is coming from. Clearly, people who sell 10 watt lasers have some kind of an agenda to convince people that their 10 watt laser is as good as a 33 watt laser. It's wrong. And you can see it in the data here. The energy density that we measured, or calculated rather, from a 5 watt laser through 10, 20, 33 goes up as you would expect. So a 33 watt laser has roughly 4 times the energy density of a 5 watt laser. You can also see the cutting speed has improved greatly, and the only reason it has improved is because the power has gone up. A 33 watt laser is almost 10 times as fast cutting material as a 5 watt laser. So you can see it, it's true. People have to stop talking about this. All right, myth number 2, which I've just brought up on the screen here, is also one that disturbs me. It's a bit harder to disprove based on our data, but I'll explain why it's not true. And myth number 2 states this: adding more diode lasers makes the beam size bigger. And I don't know where this comes from. There's this perception that there's some mystical power that's required to get all these diodes lined up inside the laser module. We live in 2023. We have engineering that can generate accuracy down to the picometer. So, you know, we don't have alignment problems with lasers. But if you look in the data, you can say, hey, this might be true. If you look at the 5 watt, it definitely has a smaller beam size than the 33 watt. But we need to understand why that's true. Okay, so to understand this, I brought up this diagram, and it's really a tale of 2 lasers. The one on the left is a laser with a short focal length lens, and the one on the right has a long focal length lens. Now, you might wonder why you'd want to do this. Well, if you look at the dark blue rectangle on each of these, you can see that on the short focal length lens, it's much smaller. It's shorter, it's narrower, and on the one on the right, the long focal length lens, it's longer and wider. Now, why do we care about this? Well, if you have a 5 watt laser, there's not a lot of power there, and we saw this from the energy density calculation. It's about a quarter of what the 33 watt laser has. So you really need to get that package of light pinched down as tightly as you can. So you use a short focal length lens. The side effect of that is the beam gets smaller, that actual spot size. And you need that because you need to get all that energy pushed down into that tiny spot. The downside is the beam doesn't cut as deep. And we'll talk a bit more about that in a future myth in a few minutes. But with the longer lens, we can use a 33 watt laser, because with a high power laser, you really want to get that ability to cut deep. So you need that longer lens to get that length. But the side effect there is the beam spot size gets bigger because the usable area of the beam is wider. And that's what's happening here. It doesn't mean that the one with the big beam is worse, or it certainly doesn't mean anything that there's an alignment challenge with all these diodes. It just means that we have different optics. Now that discussion is a good segue to myth number 3, which is increased beam size somehow makes the output worse. It makes the kerf bigger, it does something. Well, again, that's not true. You can see from the kerf numbers here that the 5 watt laser with the single diode has a kerf that is almost 1/4 millimeter, whereas some of the other numbers here are much smaller, including the 33 watt laser with that quote-unquote huge beam size. The kerf is actually smaller. Again, we need to understand why. Well, part of it is, again, because of that short lens, the beam is much more conical as it's hitting the material, so the kerf gets bigger. It's just that simple. Because the actual spot size of the focus might be 0.06 millimeters square, but where it first hits that material, or as it's digging down into the material when it's cutting, it's creating a beveled edge. And that's why the kerf on a 5 watt laser could potentially be bigger. Where, by contrast, the longer, narrower focus of the 33 watt laser means that the sides of the cut are much more parallel, and they're not perfect, again, because the lens is actually creating a cone, but it's much more parallel than it certainly is for a 5 watt laser. Okay, we're dispelling myths like crazy here, and we're at myth number 4, which is this one. Adding more diode lasers causes a loss of power. This doesn't seem right to me. I don't know about you, but I have heard YouTube content creators say this exact thing, and they are lying to you. I don't know if they know they're lying. Maybe they just don't understand. And the reason is, again, if you look in the table down below, you will see that a 33 watt laser with 6 diodes in it versus a 5 watt diode with 1 diode has many times the power. The energy density is 4 times, the speed will go up. So it's a lie. Now we need to understand why. So what I did was I created another diagram here, and this is a stacked laser. So there's 4 diodes working together to create what is going to be like a 20 watt laser. In theory, it's 24 watts, but you can see every time the beam hits some kind of reflector, it's going to lose some of its power. There will be some that just doesn't get reflected. And the exception might be the very first mirror at the top. If that's a solid mirror, we won't lose that 4%. It will get 100% reflected, or 99 point something. But let's assume that we're going to lose some of that. Now, when that beam hits the back of the next beam integration down, that one is actually a translucent reflector. It's got coating on one side, on the inside of it to do the reflection for diode 2, but it allows the beam from the top to pass through. But when it hits the glass there, it's going to reflect a bit and it's going to lose some power, and so on down the line. Now, if you add all of these things up, you'll find that it works out to, we're going to lose about 16% probably, which coincidentally works out to, in the case of a 4 watt stack, works out to about 4 watts. So that's where the power is going, and you will lose some every time you pass through an optic. Again, when we hit the lens, some of the beam that hits the lens is going to be reflected all over the place, so we're going to lose a little bit there on the way out as well. So that's what's happening. In the end, you're not going to lose anywhere near the power you added by adding a second diode, or a 4th diode in this case. So, the claim that the power will be reduced by adding diodes is a very dubious claim. It's just not going to happen that way. So we're at our 5th and final myth here, and it's this one. Higher power lasers can cut deeper. Now, certainly if you look at the ACMER P2 review I did just recently, and if you haven't seen it, you can click up here. That laser is a 33 watt laser. It can cut a 29.5 millimeter thick piece of acrylic. That's amazing. But the power isn't the only reason that's happening. Go back to the laser diagram I showed you earlier, and I'll pop it back up here. This laser uses a longer focal length lens, and that means that the package of usable laser light for cutting is longer. That means by definition it can cut deeper. And that's the sole reason this is happening. The 33 watts of power, that's what enables it to cut acrylic in the first place. It's the length of the lens that makes it cut deeper. And it's physics, it's not a power thing, it's just simple optical physics. And that should be enough to dispel this myth. Okay, so there's 5 significant myths that are dispelled, and these are things that I've literally heard other YouTubers say. If you continue to watch those channels and they say these things, unsubscribe from those channels, because they're either trying to lie to you or they don't know that they're lying to you, which is maybe even worse. Subscribe to my channel. I will always endeavor to tell you the truth. And the reason is because I don't guess. I like data. I like to measure things. And here's the proof. You saw a table. You saw the tests I did. You can do these tests on your own. And it's as simple as that. Now, if you do want to understand material testing, I'd suggest the next video you should watch is this one up above. And get out there and make your world, and I'll see you next time.